We made it to the end of the chapter. So this is section 3.8, the 8th subsection of sequences and series for the year 13 A-level, pure. So let's have a look at how we can apply series and sequences in context. So we've got the groundwork, we know how they all work in terms of the theory. Now let's have a look at the questions in terms of practice and real-life examples of how we might use the theory we developed in the previous 7 lessons. Before we do that though, there are some warm-up questions to attempt, as ever. So here they are, 1, 2, 3 and 4. So press pause now, write them down and attempt them on your own. And when you're ready to see the solutions, press play and I'll guide you through them like I normally do. Okay, so with that in mind, let's have a look at the solution to warm-up question 1. We're asked to find, using algebra, all real solutions to this equation 3b to the 4 plus 5b squared equals 22, leaving our answers in exact form. The first thing to notice here is the powers of the variable. So power 4 there and power 2 there. Importantly, what we need to note is the higher power is double the lower power, and that is a big warning light to tell us that what we're dealing with here is known as a hidden quadratic. It's a quadratic in disguise, is another way your teacher may have explained these to you. So my tip here is to substitute in the smaller power with big X. So this is b squared. So I would say let big X equal b squared. And what we'd have, b to the 4 is b squared squared. It's big X squared. B squared is just big X, and that equals 22. We can now subtract 22 from both sides to give 3x squared plus 5x minus 22 equals 0. This will now factorize. So we need to find two numbers which will multiply to minus 66. If you bear with me for a second, I'll explain why, and add up to 5. The trick I'm going to use here is as follows. What I'm going to do is I'm going to shove the 3 next to this minus 22 and multiply them. This method of factorizing you may not have seen, so I just think this is a good opportunity, a good excuse to show you how this works. So think of it as x squared plus 5x minus 22 times 3 is minus 66. Now, like I say, think of two numbers that multiply together to give minus 66 and add up to 5. Well, those two numbers would be positive 11 and then minus 6. But of course, that 3 can't have vanished into thin air, so we put it back by dividing each of these constant numbers by this number. So if it can divide, we do divide. So we can do 6 divided by 3. That gives us 2. Try and simplify this, and once it's simplified as low as it will go, if we have a non-unit denominator, in this case it's still 11 over 3, we just shove the denominator back next to the x and leave the numerator on its own. So now we have over here 3x plus 11. And that's a quick trick in terms of factorizing an expression like this. So this factorizes to this, which of course we're told is equal to 0. So therefore, if this bracket's equal to 0, we'd have that x equals minus 11 over 3. Or if this bracket's equal to 0, it must be that big X is equal to 2. But of course, big X doesn't really exist. We're talking about b squared. So b squared equals minus 11 over 3, or b squared equals 2. We're wanting real number solutions. So in terms of the real numbers, we can't have something squared which is negative. So we reject this option here Therefore, our solutions lie entirely within this idea that b squared must equal 2. So if we square root both sides here, we get b equals the square root of 2, or indeed negative square root 2. So always remember both positive and negative square roots. You need to consider both positive and negatives. That's often forgotten, even at A level, never mind GCSE. That's the first one done. Let's now have a look at warm-up question 2. So for number 2, we have this awkward looking thing here, 81 to the power x times 3 to the power y equals 1 over 27 root 3. We need to express y as a function of x. Now, the key here is if you look at 81, 3, 27, these are all powers of 3. So first thing, we can rewrite 81 to the x. 81 is 3 to the 4. So we can say that's 3 to the 4 to the x. That's the first step I'd suggest. Next, we can multiply that by 3 to the y, like so. And this here, 1 over 27 root 3, again we can simplify, because 27 is 3 cubed, and the square root of 3, the square root of anything just means power half. So again, we can simplify this bottom into this form here. Next, we can invoke the laws of indices. So here we have a power of a power, so we multiply the 4 by the x. So 3 to the power 4x times 3 to the y equals 1 over 3 to what power? Well, we're multiplying powers of 3. And when we're multiplying and the base value is the same, we simply add the powers together. So 3 plus a half is 3 and a half. 3 halves is 7, so 3 and a half, I mean to say, is 3 and a half, which is 7 over 2. But if we have the reciprocal of this, that's the same as saying it's 3 to the power of minus 7 over 2. Now you notice these base values are all the same. So we've got 3 here, 3 there, equals 3 to the power something else. So we can neaten this up slightly before we consider the solutions to it. On the left, we're multiplying 3 to the power of something times 3 to the power of something else. So this can be consolidated into a single power of 3. So we have 3 to the power 4x plus y equals 3 to the power minus 7 over 2. The bases are the same. One side's equal to the other. If that's the case, the only solution is that if the bases are the same, one side's equal to the other, the powers must also be the same. So therefore, 4x plus y must equal minus 7 over 2 in this pretty pink colour. Then a simple rearrangement to make y the subject, and we've got the question cracked. So subtract 4x on both sides. We have that y must therefore equal minus 4x minus 7 over 2. So the key point here, get the base values to be the same. Next, let's have a look at warm-up question 3. Number 3 is just conceptual. If you understand the concept, this will be easy as pie. If you don't quite see the concept, it'll be almost impossible. I'll explain what I mean. So what we have here is a graph of y equals x squared shown in blue for when x is equal to or greater than 0. So it's just y equals x squared in the first quadrant. P, xy, this point here, is on the curve. The rectangle shown shaded above, this dark one here, has height y and width delta x. Calculate the limit as delta x approaches 0 of the sum from x being equal to 2 up to 4 of x squared multiplied by delta x. This is one of the key ideas of calculus. So as delta x approaches 0, then the sum from 4 to 2 of x squared delta x, that approaches the limiting value where we can consider the actual integral. So this sigma becomes a summation, a calculus summation, between the limits of 4 and 2 of x squared, and delta x we can replace with dx. And so essentially we're integrating. This here is another way of writing the expression for the exact area underneath this curve between when x is 2 up to when x is 4. As long as you remember the basics of integration, the rest should be relatively straightforward. So what we need to do here is simply add 1 to the power of x. In this case, x becomes x cubed. We divide by the new power. But we sub in the limits of 4 and 2. So x cubed, when x is 4, is 64 over 3, obviously. Minus off when we sub in the lower limit. So when x is 2, 2 cubed is 8. Again, over 3. 64 thirds minus 8 thirds gives us 64 thirds. And again, once you spot this idea, this can be easily class-wizzed as follows. So what we could do here is we type in the integral button, press the limits 4 and 2, press x, this button here, or even x squared if you want to do it directly, x squared dx, press equals, and you will see it's 56 thirds. The final warm-up question, question 4, is Powell plays pool. And pool is a game in which games are either won or lost. He assumes each game he plays against Rob is independent, and he knows from past experience that winning each game against Rob has a 2/5 chance. He has a 2/5 chance of winning when he plays Rob. Powell plays 20 games against Rob. Calculate the probability Powell will win at least 6 of these games. What you need to infer here is if it's pool, it's either win or lose. Each game is independent, have a fixed number of games. This is going to be a binomial distribution. That's the key spot that you need to make. It's going to be a binomial distribution model. So for part A, if we let x be the distribution of games Powell wins, then in 20 games, the number of games he wins will be a binomial distribution where we've got a maximum of 20 he could win. The probability of each win is 2/5, which we can say is 0.4. To be honest, you can leave it as 2/5 if you want, that's absolutely fine. For part A, we need to work out the probability that he wins at least 6 of these games. So we need to work out the probability that his wins are 6 or greater. Now, probability tables and the probability function on the calculator is based off the inequality symbol facing the other way. So probability of winning 6 or more is everything apart from the probability that he wins 5 or fewer games. So we need to rewrite it in this form here. So on the calculator, on the class words, I'll show you how to type this in. Because we have an inequality here, we're going to use binomial CD function, cumulative binomial. So press menu, we'll go to option 7, distribution, press equals. Now here we need to scroll down till we see binomial CD, press 1, press 2 for variable. Now we type in what we need. We're trying to work out probability it wins 5 or fewer games. So what's the chance of winning 5 or fewer out of 20? That's what we're typing first. P is 0.4. Press equals and equals again. We get 0.12559 and so on. So it's 1 minus 0.125598. So we work this out, which was this value here. So now we can actually just see what this is. So if I go back to normal mode, press 1 minus that answer I just worked out, and get 0.874. In fact, I can give it to more decimal places if I want. I'll give it to 4 dp, 0.8744. Part B, this is like a binomial within a binomial, part B. So it says over a year, Powell plays 6 sessions of 20 games against Rob. Now we've already worked out what it is for playing 20 games and winning at least 6. So for part B, we need to find the probability that Powell wins at least 6 out of 20 games on exactly 3 of these 6 sessions. So now it changes. So if we let now, I'll go for variable y this time so it's not duplicating what we've used before. If I let now y equal the number of times Powell wins six or more out of 20, then we can model this one as y following a binomial distribution, where you're playing 6 sessions of 20 games. So he's playing 6 of these sessions, with the probability from part A that he wins 6 out of 20 on any one occasion is 0.8744. So now we can work out probability that y equals exactly 3. So we have this value from before. We can use this value exactly by just pressing ANS, so we don't have any need or worry for any rounding error. So go to Menu, Option 7, press equals. This time, because we want x or y in our case equals a particular value, we can use just the normal binomial PD function. Press 2 for variable. We want to work out that exactly 3 out of those 6 sessions, he wins 6 or more of the 20 games. So now we're going to press ANS. It generates it for us. So press equals. We can see here we get 0.0265 to 3 significant figures. 0.0265. That seems low, and that reason is because he's actually much more likely to win 4, 5, or even more likely to get 4, 5, or 6 times out of 6 sessions where he wins at least 6 games. So he's more than likely of winning that many games or more, with sessions where he does better than 6 out of 20. Let's now have a look at modelling real-life problems using sequences and series. So let's just get straight into it. So this first one. At the beginning of each month, Kath places £100 into a bank account to save for a family holiday. Each subsequent month, she increases her payments by 5%. Assuming the bank does not pay interest, find the amount of money in the account after 9 months. So let's think about what this sequence or series looks like. She puts £100 in first. Next, she increases it by 5%. So the next payment would be 100 times 1.05. The next payment would be 100 times 1.05 squared, and so on. So after 9 months, what's going to happen is the sum after 9 months is going to be A, just remind you, Sn equals A brackets Rn minus 1 over R minus 1. So this here is a geometric progression disguised in a worded question. So the first term, A, is 100. The common ratio, well, it's increasing by 5%, so the common ratio we're multiplying by 1.05. After 9 months, so n is 9, minus 1, then divided by 1.05 minus 1. So press equals and see what we get. So it's going to be 100 and brackets 1.05 to the power 9, subtract 1 of course, all divided by 1.05 minus 1, press equals. We get, to the nearest penny at least, £1,102 and 66p. Part B, we're told month N is the first month in which there is more than £6,000 in the account. We have to show that N is greater than log 4 divided by log 1.05. So what we need to do is find the sum of the first n months. So using this formula here, because of Sn is A Rn minus 1 over R minus 1, and that has to be greater than 6,000. So if we just plug in the numbers, like I said earlier, like you can see, the first term is A, the common ratio is 1.05, and our job is to find what n is. So if we just plug these values in, so we're going to get 100, 1.05 to the n minus 1, all over, well 1.05 minus 1 will give us 0.05. That has to be greater than 6,000. So 100 divided by 0.05, what does that give us? Well, 100 divided by 0.05, that gives 2,000. So this means we've got 2,000 brackets 1.05 to the n minus 1 must be greater than 6,000. We can now divide both sides of this by 2,000. So if we just take this here, divide by 2,000, we get 1.05 to the n minus 1 is greater than 6,000 divided by 2,000, which gives us 3. If we now add 1 to both sides, we see that 1.05 to the n is greater than 4. Now we can take logs of both sides. So log of 1.05 to the n is greater than log 4. But of course, if we take logs, we can bring the power down to the front. So that gives us n multiplied by log 1.05. I apologise for my trying to squeeze everything into a tiny space here. I should really have set it out clearer, but I hope you can still follow my logic. And finally, we can isolate n by dividing through by log of 1.05 to see that therefore n must be greater than log 4 all over log of 1.05, just like we wanted to prove all along. The final step now for part C is we want to show that how much Maggie needs to increase her payments by if she wants to get to £6,000 in 29 months. Maggie, as it happens, is saving us the same time as Kath. She puts £50 into the same account again and again and again, and she's planning to increase her payments by a constant amount each month. So let's think about what this means. So for the first month, this Maggie character would put £50 in. So let her monthly increase, let's call that a letter. So the monthly increase, I'll call that D, because D is a letter we use in the sum of an arithmetic sequence. Let monthly increase equal D. So then we have 50. The next month would be 50 plus D. Then she has that difference again for the next month. I'll put this in brackets so you can see the difference in months. First month, second month, third month, fourth month, and so on and so on. You get the idea. So that keep on adding together. That needs to come to 6,000 in 29 months. So in 29 months, the last term, obviously you see here when it's the second month, it's 1D. Third month, 2D. Fourth month is 3D. So it's always one less the number of Ds. So the 29th month will be 50 plus 28D. So that's the sum of the first 29 months. And we want that to happen within the 29 months. In other words, this sum needs to total £6,000. Now this here is an arithmetic progression. So the first term is 50. The common difference is obviously literally D. I chose it to be the same. And the number of terms is 29. So the sum of these 29 terms is always n over 2, using the formula, 29 over 2, brackets, 2 lots of the first term, so 2 times 50, plus n minus 1 multiplied by d, and we know that needs to equal 6,000. We just plug in the numbers we know. So Sn equals n over 2, brackets 2a plus n minus 1 d. That's a formula you are told, but hopefully by the end of this chapter you're familiar with. We can now neaten this up quite a lot. So first off, what we can say is 29 over 2 times 2, that'll cancel. So 29 over 2 times 2 times 50, we can just do it on the calculator, to be fair. So 29 over 2 times 2 times 50, we get 1450. Now 29 minus 1 is obviously 28, so 28 times 29 over 2. Gives us 406. So 1450 plus 406 lots of D equals 6,000. I can then subtract 1450 from both sides. I then get 460 equals 4,550. Finally, divide both sides by 406. D must be 4,550 divided by 406. Let's see what this gives us. So 4,550 divided by 406. That gives us, apparently, £11 and 21 pence to the nearest penny. Let's do another one. So this one we're talking about a sports car. The maximum speed in miles per hour that can be achieved in each of the 5 gears of a sports car form a geometric progression. The maximum speed obtained in first gear is 32, while the car can achieve a maximum speed of 162 miles per hour in 5th gear. Find the maximum speed that can be achieved by the car in third gear. So for this one here, we need to remember for a geometric progression, un equals ar to the n minus 1. So let's just fill in what we know. So for first gear, you can get to 32 miles per hour. So u1, which is 32 miles per hour. The first term's a, r, 1 minus 1, ar to the 0, 32 is just 32. So in fact we don't need to say anything else about that. The first one's 32. And that's just going to be equal to a. Now, we're told here in fifth gear, it can go up to 162 miles per hour. So U5 equals 162. That's AR to the 5 minus 1, which is AR to the 4. So this one now, if I do U5 divided by U1, I'll get 162 divided by 32, 81 over 16. And then AR4 divided by A, give me R to the 4. So for a common ratio, will be plus or minus the fourth root of 81 over 16, which is plus or minus 3 over 2. But of course, the speed doesn't go from 32 then down to a minus, so the common ratio has to be positive. So the common ratio R must be 3 over 2. So for third gear, that's when U is 3, U, the third term rather, that's going to be the first term, A, which is 32, multiplied by the common ratio, which we now know is 3 over 2, to the power of 3 minus 1, which if you want to just put squared is absolutely fine. But now we can work this one out. So 32 times 3 over 2, all in brackets, to the power, just put 2, get 72 miles per hour. Final one, worked example 3. So worked example 3, we have a liquid which has been kept in a barrel. At the start of the year, the barrel is filled with 160 litres of liquid. Due to evaporation though, at the end of every year, the amount of liquid in the barrel is reduced by 15% of its volume at the start. So part A, calculate the amount of liquid in the barrel at the end of the first year. So if it reduces by 15%, that's another way of saying 85% remains. So quite simply, at the end of the first year, it'll be 85% of its former self. To find 85%, I just multiply by 0.85. So what's 160 multiplied by 0.85? That gives us 136. That's 136 litres. Part B, again, isn't too hard really if you think about it. Show that the amount of liquid in the barrel at the end of 10 years is approximately 31.5 litres. This is like a compound depreciation question. So for 1 year, it's multiplied by 0.85 just for the 1 year. So essentially just an invisible 1 here. So for 10 years, it's going to be multiplied by 0.85 to the power 10. It's going to reduce by 15% once, twice, 3, 4, 10 times. So if we work this out, we can show what needs to be shown. So 160 multiplied by 0.85 to the power 10, that gives us 31.4999, which indeed is more or less, damn it, 31.5 litres, as required. Part C, It says at the start of each year, a new barrel is filled with 160 litres of liquid, so that at the end of 20 years, there's going to be 20 barrels containing liquid, and each barrel will have different amounts of liquid kept inside it. So calculate the total amount of liquid to the nearest litre in the barrels at the end of the 20 years. Let's think of this in terms of a table. We have different things going on. So we're going to have the barrel number and therefore amount of liquid. So there's going to be 20 different barrels. So if I take 1 to be the first barrel, the first one on the scene, and the 20th to be the last barrel that comes along, we can think about a pattern and see if we can find out, by appealing to patterns, what's actually going on. So the first barrel, second, third, fourth, 20th. Well, the first barrel, it reduces by 0.85 to the power 10 after 10 years. So with the first barrel, if it's been around for 20 years, that will have reduced to 160 multiplied by 0.85 to the power 20. The next one, if I came onto the scene a year after, that will have reduced by 0.85 to the power 19. The next one will have reduced by 0.85 to the power 18. And by now, you should have seen a pattern forming in your mind in terms of how these numbers and values are working. And finally, the last barrel, the 20th year one, will have just reduced by 15% once at the end of its first year. So if we total all these up, we can factorise out this 160 and start with this one first, start with 0.85 and build back up. So 0.85 plus 0.85 squared plus 0.85 cubed, all the way up to 0.85, obviously, to the power 20. Whoops. That's my unsteady hand. So, the thing is, this bit here is actually, as you can hopefully gather, a geometric series. So this is a geometric series. The first term, A, is 0.85, which is also the common ratio. We're multiplying by 0.85 as we move from one term to the next. Now the number of terms here, 1, 2, 3, 4, all the way up to 20. We've got n being equal to 20. So this one here, the sum of these 20 terms is going to be 0.85 brackets 1 minus 0.85 to the power 20 all over 1 minus 0.85. So please help me, calculator. 0.85 brackets 1 minus 0.85 to the 20 all over 1 minus 0.85, about 5.447. So all of this thing here, which is a geometric series, sums to approximately 5.447. So therefore the total liquid will be this 160 multiplied by this 5.447 figure, which we can calculate by just multiplying our previous answer by 160. So we get 871.5 litres, but to the nearest litre, 872 litres. And we're finally done. So here are the questions I'm going to recommend you try. Page 84, exercise 3I, the whole thing if possible, Pure Maths Year 2 book. These questions on modelling are becoming increasingly common in the new spec, so knowledge of how to tackle these will really serve you well for the real thing, dare I say. Thanks for listening. Once again, I do hope you find some of it useful. If you're stuck, please do let me know, and do indeed take care of yourselves until next time. So keep safe, and I'll see you soon. Goodbye for now.